Okay, welcome to the deep dive. Today we're diving deep into something specifically curated for you based on a stack of source material. It all focuses on the CompTIA DataX exam. That's the DY0-001.
That's right. And what we have is basically a collection of practice questions, and importantly, the explanations behind the answers for this exam.
Exactly. And our mission here really is to kind of cut through to the core knowledge points, the stuff hidden inside these practice questions.
Sort of like a shortcut.
Yeah, a shortcut to understanding some fundamental concepts in, data handling, data analysis.
We're hoping to uncover practical insights into the kinds of challenges data professionals actually run into and how to think about solving them.
Straight from the material that tests that knowledge. So let's unpack this together.
Okay, so first off, the source material itself gives a little context about the exam. It mentions it's in English, uses multiple choice, and interestingly, performance-based questions.
Performance-based, huh? So not just ticking boxes.
Right. Up to 90 questions, 165 minutes. It just frames what kind of knowledge they're testing, practical, applied stuff, not just abstract theory.
Makes sense. They want to know you can actually do something with data.
Hmm.
And looking through these questions, yeah, you see that right away. Let's maybe jump into the first one. It really highlights a common headache in data work.
Missing information.
Bingo. Dealing with missing info. So this question sets up a scenario. You've got numerical data, some values are missing, but the key part is the data has a skewed distribution.
Okay, not a nice symmetrical bell curve.
Exactly. And it asks, what's the best way to handle those missing numerical values given that skew?
And the options they give are, pretty standard things you might think of. Using the median, just dropping the rows entirely, using the mean, or maybe replacing with zero.
Right. And the source material points directly to using the median. Imputing with the median is the correct answer.
Okay, so why the median? Why is that the hero here, especially with skewed data?
Well, it's fascinating because the data characteristic, the skewness, it completely dictates the best move.
When data's skewed, right, it means you've got a long tail on one side, some extreme values pulling things.
Yeah.
And the mean, the average, is really sensitive to that. It gets pulled way over towards the extreme value, so it stops being a good measure of the typical value.
Like the classic example,
Yeah.
average income in a town. One billionaire moves in, the average shoots up, but it doesn't reflect most people's reality.
Exactly. But the median, the middle value, if you line everything up, it's resistant to those outliers. It stays put.
I see.
So if you use the mean to fill in missing values in that skewed data, you're basically introducing distortion. You're filling gaps with values influenced by the extremes. Using the median, though, keeps the central tendency much more stable and true to the bulk of the data.
Okay, so the core takeaway here is missing numbers. Don't just blindly use the average. First, look at the shape of your data. If it's lopsided, skewed, the median is probably your best bet for filling those gaps without messing things up.
Right. And why should you care? Because getting this wrong at the start, well, it can throw off your whole analysis or model downstream.
Definitely. Which actually leads pretty well into the next kind of practical problem these questions cover.
Evaluating models.
Yeah, evaluating how well your predictive models are actually doing their job. This specific question asks about checking the accuracy of a regression model.
Regression models.
About
Those are the ones predicting a continuous number, right? Like house prices or delivery times, that kind of thing.
Exactly. Not predicting a category like spam or not spam.
Yeah,
That's classification.
got it. So for regression, the options given for the best overall accuracy metric were plain old accuracy, root mean squared error, or RMSE, F1 score, and log loss.
And the source says the answer is RMSE, root mean squared error.
Okay, RMSE sounds a bit technical. What does the source say it actually, does?
So the explanation highlights that RMSE measures the average size, the average magnitude of the errors.
Okay.
It tells you, sort of on average, how far off your predictions are from the real values. But the key bit is the squared part in the name. That means it gives much more weight to the bigger errors. If your model is way off on a few predictions, RMSE gets hit hard, much more than if it had lots of tiny errors.
So it really penalizes those big mistakes. Makes sense.
Precisely. It's seen as a good, robust summary of a regression model's overall predictive power.
And the source also explains why the others don't fit here. Accuracy, F1, log loss, those are really designed for classification problems, judging categories.
Yeah, that distinction feels really important. It's not one size fits all for metrics.
Definitely not.
So the core point, predicting a number, regression, you need a metric like RMSE that gets how far off you are. not just a simple right or wrong like in classification.
And why does this matter to you, the listener? Well, if you're building any model that predicts a number, you absolutely need the right yardstick to know if it's any good.
And where it might be making the biggest blunders. RMSE helps with that.
Okay, switching gears a bit, but still super critical. Data privacy, another major theme in these questions.
Oh yeah, hugely important. This question described a data scientist with user data, and crucially, it contains personally identifiable information PII.
Right, the sensitive stuff. Names, addresses, emails, maybe even more sensitive things.
And it asks, what's the absolute first thing they need to do?
The options were kind of interesting. Things like build your model first, then worry about anonymizing the results. Or remove or anonymize the sensitive fields up front. Or maybe use fancy neural networks hoping they handle it. Or just compress the data.
And the source is crystal clear on this one. The very first step before you do anything else is remove or anonymize those PII fields.
Yeah, the explanation really hammers this home. Protecting privacy isn't an afterthought, it's step one. It has to happen before analysis or modeling even starts.
It's not just good practice either, is it?
No, often it's a legal requirement. Think GDPR, CCPA, those kinds of regulations. By getting rid of or masking the PII first, you make the dataset safe to work with. You can analyze patterns without compromising who people are.
So it's not a cleanup step you do later.
Yeah.
You don't rely on algorithms to magically protect it. It's fundamental, ethical, often legal, right at the start.
Absolutely. The core knowledge. Protect privacy, handle PII first. It's non-negotiable.
Which really brings up that constant balancing act, doesn't it? How do you get insights from data while fiercely protecting individual privacy?
And this question gives a very direct answer for that initial stage. Start by removing or anonymizing the PII.
Makes sense. Okay, speaking of understanding data, visualization is key, right?
For sure. There was a question asking about the best chart type for showing the distribution of a single continuous variable.
Like wanting to see how heights are spread out in a group or maybe test scores.
Exactly. And the options were bar chart, scatter plot, histogram, and line chart.
And the source gives a very definite answer, histogram.
Okay, histogram. Why that one? What does it show that the others don't for this specific task?
Well, the explanation points out that a histogram is basically purpose-built for this exact job.
How so?
It takes your continuous data, say all the height measurements, it divides the whole range of heights into intervals or bins.
Okay, like 5'0" to 5'2", 5'2" to 5'4", etc.
Exactly. Then it draws bars showing how many data points, how many people fall into each height bin.
Ah, so you instantly see the shape, where the values cluster, if it's symmetrical, skewed, if there are gaps.
Right. You can see if most people are around average height, or if you have distinct groups of tall and short people.
And the other charts?
Well, a bar chart is usually for comparing counts of distinct categories, not continuous spread.
Like number of people in different departments?
Yeah. A scatter plot needs two variables to show their relationship. A line chart usually shows trends, often over time.
So none of them really nail showing the distribution, the spread, of just one continuous variable like a histogram does?
Exactly. Core knowledge point. Want to see the shape of your continuous data. Histogram's your go-to tool.
And why care? Because picking the right chart makes understanding data way easier, way faster. A histogram answers that fundamental question. How is this numerical data spread out?
Nicely put. Okay, one last practical problem area that came up in these questions. It involves making decisions when you have limits or rules.
Constraints.
Yeah. The question described a company trying to minimize delivery times for its trucks. But crucially, they had to factor in things like traffic patterns and maybe road restrictions.
Real-world stuff.
Totally. And it asked which approach is best suited for this kind of problem.
Their options were decision trees, clustering, neural networks, and something called constrained optimization.
And the source identifies constrained optimization as the correct answer.
Constrained optimization. I mean, the name itself sounds like it fits the problem perfectly, doesn't it?
It really does.
Yeah.
Optimizing something, minimizing time under constraints, traffic, roads.
And the explanation confirms that intuition. Constrained optimization is basically a whole field of math and computation focused on finding the absolute best solution, whether that's minimizing cost, maximizing profit, minimizing time, whatever, while strictly following a defined set of rules or limits.
Like finding the quickest delivery route that also avoids certain roads at rush hour, or keeps heavy trucks off small residential streets.
Exactly. You have a goal, quickest route, but you also have boundaries you cannot cross. Road rules, traffic.
And the other methods mentioned, decision trees, clustering, Neural nets?
They're powerful for other things, definitely, like making predictions, finding groups or patterns in data. But they aren't specifically designed to find an optimal solution within a set of hard constraints in the same direct way.
So the core knowledge point here is recognizing that when your problem is about finding the best outcome, but you have strict rules you must follow, there's a specific toolbox for that, constrained optimization.
And why does this matter? Well, think about it. Most real-world problems aren't wide open. You usually have limits.
Budgets, time, resources, physical laws.
Exactly. So knowing that there are dedicated techniques for finding the best path within those limits is super valuable. How often in your own life, outside of data work, do you run into situations where the best thing you could possibly do is limited? Limited by constraints like your budget or the time you have available, or maybe rules you have to follow, or even just the needs of other people?
Constantly, right.
Probably. So the thought is, how might actually thinking about finding the optimal solution within those boundaries, or even just consciously considering the distribution of your choices, how might that change the way you approach making those everyday decisions?
That's a really interesting angle. Applying constrained optimization thinking to life.
Something to ponder, maybe?
Definitely something to ponder. Keep exploring, everyone. Keep questioning.